Okay, our next speaker for today will be Szilárd Pfeiffer. There will be time for Q&As after. Directly after that, we will visit for lunch and everybody back 1300. Szilárd.
Okay, my name is Szilárd Pfeiffer. I would like to dive into the details of cryptography protocols in this presentation before the lunch. I hope so that the late will be not so much. So I graduated as an electrical engineer almost 20 years ago. Since then, I have been working in the IT security sector. I started my career as a software developer, and now I am a security engineer and evangelist, as you can see on the slide. I work at the Logbased, which is one of the few Hungarian IT security vendors. Formerly, this company was called Logbased. Logbased was the vendor of the well-known Szilárd, and Logbased now is the vendor of Zolb application level firewall, which is an open source edition called Zolb GPL. This story has begun with my pet project, Cryptolyzer, which is a cryptographic settings analyzer. Its functionality is similar to the SSLIs and testSSL.sh and SSL scan. When I started this project, I wanted to skip or forge the cryptographic part of the TLS handshake because I wanted to save some resources. I realized that it is possible to send seemingly cryptographically correct messages to servers which are accepted by them and answered by them. Why is it a problem? Is it a problem because these messages are short, simple, and these messages can be prefabricated? In turn, you can enforce the server to do the CPU-intensive part of the TLS handshake. So with relatively low bandwidth, without almost zero computation on the client side, you can enforce the server to do significant amount of CPU computation. So it seems like an exploit. But my question was that how generic this exploit? All cryptographic protocols have a step called key exchange. What is key exchange? When parties want to communicate in a secure way, they need a secret, a shared secret, a shared key. This shared secret is just a random number, random data. It will be used to encrypt and decrypt messages in a symmetric way. This shared secret is key, must be exchanged without risking it is compromised by a third party. And this key must be exchanged on an untrusted channel. Fortunately, there are some algorithms which can do that work. First of all, I have to mention the good old Diffie-Hellman key exchange. Diffie-Hellman key exchange have some advantage. For instance, it is so elegant and so reliable, but it has some disadvantages. For instance, it needs a significant amount of CPU computation. And this amount of CPU computation increases along with the key size. There are some other algorithms, just like RSA, but RSA requires less computation on server side and more computation on client side, and it is a little bit complicated, so it makes it less effective to perform an attack. There is an elliptic-curve based version of the Diffie-Hellman key exchange, which requires much less computation both on server and client side, so it is not so effective to perform an attack. So the most exploitable one is the Diffie-Hellman key exchange because it requires a significant amount of CPU computation on server side, and it is so easy to enforce by some messages. Okay, the question is, well, so in practice, I want to use it in practice, not just in theory. So I was interested that how generic this problem can be. Diffie-Hellman key exchange is so widespread. It is used not only in TLS, but also in other cryptographic protocols, just like IPsec, OpenVPN, and SSH. In case of TLS, we use it to provide backward compatibility when the forward secrecy is important. Forward secrecy is a property of key exchange algorithms, which means that if the master secret is compromised, the encrypted messages cannot be decrypted. It is true if we are talking about the ephemeral version of Diffie-Hellman key exchange. So the Diffie-Hellman key exchange protocol is still used because it can provide backward compatibility and it has the property forward secrecy. So it is also used in case of SSH, OpenVPN, and IPsec because there the forward secrecy is so important. It is relatively easy to enforce the server to start the initial part of the Diffie-Hellman key exchange, which requires the CPU computation. It needs only one message in case of TLS and only just a few messages in case of other cryptographic protocols. To send these messages need low resource requirements. It requires low resource requirements because you have to send only 1 to 3 messages. These messages are relatively small, about 100 bytes or something like that. But sending these messages requires almost no computation. These messages can be prefabricated, and the message size can be decreased after you discovered the server, what cryptographic protocols or cipher suites are supported by the server. So these messages can be optimized by size. So a denial of service attack can be performed from a single IoT device. I tried it. I have a relatively old Wi-Fi router, and so it's at least 5 years old, and I tried it, and it was possible to perform an attack against relatively correct server. Key sizes are increasing and increasing, and as I mentioned, the effectiveness of this attack increases along with the key size. Now, the 2 kilobytes of Diffie-Hellman public key considered to be secure, but there are cryptographic algorithms where the client can enforce higher key sizes. In case of TLS, the key size is determined by the server, but in case of SSH and IPsec, the key size can be enforced by the client. This attack can work under the radar. I mean that it means that it generates only low-level error messages or log messages on the server, which are not necessarily recognized by an intrusion detection system. So after the theoretical explanation of that attack, I would like to demonstrate it for you. The environment will be very simple, just one client and a server. A server is a DigitalOcean instance. It has 4 CPUs and 8 gigabytes of memory. I will use 4 kilobyte Diffie-Hellman public keys because it makes the results comparable in case of different cryptographic protocols. I will run an Apache web server in a Docker container, and that it will be the server part. I created an application to perform the attack. I named it Day Heater because it can heat the CPU by enforcing the Diffie-Hellman key exchange. It depends on this application depends on my pet project called Cryptolyzer. Both the application and the dependency are available as an open source project. The Day Heater application can be available on the GitHub page of Volasys under the conditions of the Apache license. Let's see the demo. Okay, as you can see, there is a server, and I start Docker container with Apache. That's it. I will start an HTOP to see what is the result of the attack. As you can see, there are 4 CPUs. There are some Apache processes which are running. So let's start the attack. There is an initial phase to probe that the Diffie-Hellman key exchange is supported by a server. And after that, a summary is printed. And as you can see, the attack can cause 100% CPU usage on all 4 CPUs. And as you can see, the load average value is increasing and increasing. Now it's 32. And after a while, it should be increased or not. There is a problem with the internet access anyway. Yeah, as it can be seen. If the network works well, the CPU usage is constantly 100%. Let's see statistics. After I stop the application, there will be statistics, as you can see. Only 10 kilobytes per second was enough to cause 100% CPU usage on 4 CPUs. So it's a relatively low bandwidth. Let's back to the presentation. Here is a table. This application can be used not only by TLS but also by SSH. So if we are talking about TLS, if the network works well, only 6.8 kilobytes per second bandwidth is enough to cause 100% CPU usage in average. So it's a relatively low bandwidth. It is also true in case of NGINX. But if we are talking about the bandwidth, the case is the same independently from the server application. So it is the same in case of Apache. It is the same in case of NGINX. But it is significantly different if we are talking about the newly created threads. Thanks to the pretty good threading model of NGINX, no new threads can be generated by DHeater in case of NGINX. It is about the threading model of NGINX. As you can see, DHeater may seem more effective in case of SMTP protocol, but it is not true. This result is not about the effectiveness of the attack or the DHeater application. It is about the implementation of postfix. In general, we can say that this DHeat attack, is a little bit less effective if we are talking about opportunistic TLS protocols, because only one message is not enough to enforce the Diffie-Hellman key exchange. It is especially true if we are talking about the SMTP protocol, because several applications usually delays the response to the initial message to defense against spam bots. Let's see what the case if we are talking about the SSH protocol. As you can see, much higher bandwidth is required in case of SSH, but this bandwidth is still not so high. The reason is the fact that in case of SSH, you have to send at least 3 messages, and you have to receive at least 2 messages to enforce the Diffie-Hellman key exchange. But only 80 kilobytes per second bandwidth is enough to cause 100% CPU usage in average in case of OpenSSH. In case of tactile SSH, the result is much imperceived because the threading model, as I can see, the threading model of tactile SSH, how can I say it politely? less better than the threading model of Nginx. That's the case. Okay. So the bad news is the fact that the very low bandwidth is enough to overload the server. After the bad news, let's see how we can defend against this attack. There are three types of mitigation. First is protocol-based. In some cryptographic protocols, there is a mechanism called cookie. A cookie is just a random number, which is sent by the server, and the client should reply it to the server. It makes impossible to prefabricate the initial messages by the client, so it makes the attack a little bit less effective. It is still effective, but it's a little bit less effective. It requires a little bit more CPU computation because you have to compute each messages in case of each connection, but the attack is still effective. Unfortunately, in case of TLS, in 1.3 version of TLS, there is a cookie mechanism, but this is used only if the server misses some information from the message sent by the client initially. So if you send a message to a server which is acceptable for it will not require you to send a cookie back to it. In case of the older versions of the TLS, there is no cookie mechanism at all. In case of SSH, there is a cookie mechanism, but it is not about the denial of service attacks. It is about the session identifiers and keys. It makes it undeterminable, the key and the session identifier. So it is not about the denial of service. That's the case. The second level of mitigation can be application-based. There are some server applications which can be configured to reduce the effectiveness of this attack. Unfortunately, most of the application servers have no configuration to do that at all. I have to emphasize the OpenSSH and TechDSSH because they have the necessary configuration. In case of OpenSSH, you can control the maximum number of unauthenticated sessions. It is so important because the initial part of the cryptographic handshake is unauthenticated. It's just plain text. So if you can control the maximum number of unauthenticated sessions, you can control the effectiveness of this attack. But unfortunately, in case of OpenSSH, if your server is under attack, and you control the maximum number, it makes it harder to access your server which is under attack. In case of TechDSSH, you can control the connections per process, and there is a whitelist. So you can say that there are some IP addresses which are not counted into which are not controlled by this configuration. So if your server is under attack, you can surely access your server. The third level can be log-based. There is a very useful and effective tool called fail to ban to bonding clients which generate a certain kind of log messages. Unfortunately, by default configuration, servers do not generate the necessary log messages to fail to bond the malicious clients. In higher log levels, there are necessary messages which can be used by the fail to bond to identify the malicious clients and to bond them. By default, Dovecode, OpenSSH, and TechDL generates the necessary log messages. Fortunately, verbosity can be increased by module in case of Apache and Postfix, so you can increase the log level for only the SSH module. So you don't have to increase it in general, which causes that this significant amount of log messages will be generated by the application server. Unfortunately, in case of Nginx, you can only increase the log level in general. So, what are the conclusions? If you run a private service, for instance, and a VPN server and an SSH server. Yeah, I know it very well that it can be accessed from the internet, but it's private. You don't want to that everybody access it, but just a few people. So in case of private services where you can control the clients, the easier solution is not to use the Diffie-Hellman key exchange. Use only the elliptic-curve version of the Diffie-Hellman key exchange, which requires much less computation, and it makes much less effective. So it makes this attack much effective. If this is not the case, and you have to provide the plain old Diffie-Hellman key exchange, I suggest to control the number of connections which are in the pre-authentication state by application-specific settings or by fail to bomb. If you have public services, I suggest to consider the compatibility with the older clients. I mean that the major web browsers support the elliptic-curve version of the Diffie-Hellman key exchange for at least 5 to 10 years. Other type of clients also support the elliptic-curve version of the Diffie-Hellman key exchange for at least 5 years. So please consider the backward compatibility. If you have to support the Diffie-Hellman key exchange, the situation is the same as it was in case of the private services. Control the number of connections or control the number of connections cause cryptography error. You can do it by application-specific settings or by fail to ban. There is a QR code. It contains an URL, which is the GitHub page of the day heater application. Let's try it to check whether your servers are defensed against this attack. And the GitHub page contains not only of the application, but the configuration patches to fail to ban to defense against this attack. So let's try it, and happy hacking. Thank you for your attention.
Porno 3, the question is, what is the protocol vulnerability that makes this exploitable and how to fix it?
Well, okay, the protocol cannot be fixed. That's the problem, because the Diffie-Hellman key exchange works as it works. You have to, if you are a normal client, not a cheating one, you have to compute something at the beginning of the Diffie-Hellman key exchange. So the amount of the computation is the same in case of a client and in case of a server. But unfortunately, it is possible to cheat the cryptographic part. You can say that, oh, I computed what I have to compute, and you can send a fake message, which is pre-computed, and you can send this pre-computed message again, and again, the same message. So you don't have to compute anything, but the server tries to compute its part in each connection. That's the problem. You cannot fix it. You cannot defend against it. It's a protocol problem. It is the issue of the protocol. It is true in case of TLS, in case of SSH, and it is also true in case of IPsec. Thank you.